9.2 is about redox half equations or half reactions. The first part we're going to look at how to write a half reaction, and the second part is how, when given your half equations, how do you go back to a full redox equation or reaction. So first, writing a half equation. There are two steps you want to do in order to determine the half equation. Here we have zinc plus copper 2 plus gives us zinc 2 plus plus copper. First step you want to do. What we'd like to do is to determine your oxidation numbers as we had learned in 9.1. Pure zinc has an oxidation number of 0. This copper ion, since it's a simple ion, will have an oxidation number of plus 2, which matches the charge of 2 plus. Zinc ion, since it's a simple ion, will also have an oxidation number of 2 plus. And the copper atom, since it's in its pure form, has an oxidation value of 0. What you want to do now is, in step 2, is go through and figure out what's going on with each atom. Therefore, zinc is going from an oxidation value of 0 to plus 2. It is losing electrons, therefore it is being oxidized. Its half equation, therefore, is zinc breaks down into zinc 2 plus plus 2 electrons. Because it is being oxidized, oxidized means loss of electrons. In order to represent that, those electrons need to be on the product side. As for copper, copper goes from a plus 2 to a 0 oxidation value. That means it's gaining electrons, so it is being reduced. Therefore, its half equation is copper 2 plus, because that is what is in the reactants of the original equation. It is gaining the 2 electrons zinc is losing to make a pure copper atom. Again, because it is being reduced, an element that is being reduced it means it's gaining electrons, which means you need to be adding those electrons to the atom on the reactant side. What you must keep in mind during this whole process is you must have an equal number of electrons when you're breaking out the elements into their oxidation states. Here's another example. So going through each one, we have 2 Fe 2 plus plus Cl2 gives us 2 Fe 3 plus plus 2 Cl minus. Again, step 1 is to determine the oxidation value for each of your elements. So on this iron, we have a plus 2 value. On this chlorine, we have a 0 value. The following iron, we have a plus 3 value, and Cl minus has a minus 1 value. Now I'm going to take each of the atoms themselves and go through and look at what's being oxidized and what's being reduced. So if iron 2 plus, if I have iron, it is going from a plus 2 to a plus 3 value. Therefore, it has lost an electron and it is being oxidized. Chlorine is going from a 0 to a negative 1. It has gained an electron, therefore it is being reduced. So, how do we represent the half reactions? Here, we have our iron, and we have 2 of them, so 2 Fe 2 plus. It is being oxidized, so the electrons need to be on the product side to show the loss of electrons. So here we have 2 Fe 3 plus. We know we had a change of 1 electron from going from 2 to 3, but there are 2 iron. Therefore, a total of 2 electrons are being exchanged. For chlorine, Since chlorine is being reduced, we have to add those 2 electrons that iron gave up to provide each of those 2 chlorines an electron. And those are their appropriate half reactions. Now, writing half equations are relatively simple as long as you can assign oxidation values appropriately and determine that the same number of electrons are being transferred from either side of the reaction. However, writing the redox equation from its associated half equations is a little bit more complicated and has multiple steps associated with it. During this process, what we're going to be doing is to make sure that the redox equation is balanced for all of its atoms and charges that are associated with it. What we need to keep in mind is most reactions occur in acidified solutions. Therefore, we can use water to help balance any excess oxygens, and we can use H+ to help balance any excess hydrogens during the process. And you'll see an example of this as we work through it, and you will have a better understanding of what this looks like. Here are all of the steps. I'm going to just discuss what each of the steps are, and then we're going to go through 2 examples of how to use these steps. Step 1 of writing a redox equation from its associated half equations. Step 1 is to assign the appropriate oxidation values for the elements provided. Step 2 is broken down because in step 2 we want to write each half equation for the oxidation and the reduction equations. First step under that is to balance the atoms that are present. B, you want to balance any oxygens by adding waters to the opposite side. C, you then want to balance the hydrogens provided from that water by adding H+ to the opposite side. D, you want to balance your charges, your plus and or minus charges, by adding electrons to the appropriate side of the equation. Step 3, you want to then equalize the number of electrons for both half equations. Then step 4, add the half equations together, canceling out any commonalities. For the first example, we're going to look at, we have NO3 minus and Cu react together in an acidic solution to produce NO and Cu2+. Alright, as discussed on the previous slide, step 1. We want to assign the proper oxidation value to each of the atoms present above. Okay, so we know oxygen has a -2. There are 3 of them, so that's a total of -6. We need to make sure -1 stays on NO3. Therefore, nitrogen has a +5. Copper is a pure element. It is 0. Here, O has a -2. It's a 1-to-1 ratio. Therefore, nitrogen has a +2. And this copper, being in its ion form, has a +2. Alright, so who's being reduced and who is being oxidized? Going through and looking at each of these, we have N is going from a +5 to a +2. Therefore, it is gaining 3 electrons, and it is being reduced. Copper is going from 0 to a +2. It is losing electrons, and therefore being oxidized. Oxygen is going from a -2 to a -2. So nothing is happening. It's just a spectator ion in this entire process in order to help the process run. Alright, so now that we know what is being oxidized and what is being reduced, we're going to move on to step 2. Step 2. We want to write our half equations for each of the oxidation and reduction reactions. A. Balance the atoms other than your hydrogen and oxygens present, because we'll do that later. So if we have our oxidation, we have copper, and it's going to copper 2+. That one's already balanced. So let's look at our reduction. We have nitrogen, which is NO3, going to NO. Again, because we're just looking at the reduction reaction, nitrogen's the one being reduced, not oxygen, and it's a 1-to-1 ratio. Therefore, it is already balanced. This part has been made easy for us. Step B. Balance each half equation for oxygen by adding water to the appropriate side. Our redox reaction is the only one that has oxygen in it. Therefore, we are going to be changing that particular reaction. So NO3, so this is step B, and this was step A. NO3, our reactant side has 3 more oxygens than our product side. Therefore, the water is going to be added to the product side. There's 1 oxygen on the product side. We are going to need to add 2 waters. So now we have 3 oxygens on both the reactant and the product side. Step C. Balance each half equation for hydrogen by adding an H plus to the appropriate side. Again, our oxidation reaction only has copper present, so we don't need to worry about it. Therefore, once again, we're going to need to worry about our redox reaction because we added water to it. Therefore, we have NO3, and we have 4 hydrogens that we had placed over here on our product side. Therefore, we need to account for those 4 hydrogens. Therefore, we're going to write 4H plus and finish off with the NO plus 2H2O. Then step D. Here we want to balance each half equation for charge by adding electrons to sides with more positive charges. Looking at our oxidation reaction first, so we have copper. Copper is an atom, it is being oxidized, therefore it loses its electrons. We are going to write those lost electrons on the product side to show that they have been lost. For our redox reaction, because it's being reduced, it is gaining electrons. Again, we're going to need to make sure we're writing the right number of electrons, and that's going to be a little bit difficult, and I'll show you how we do this. It has to go on the products or on the reactant side. So if you remember that our original nitrogen was carrying a +5, and our nitrogen on our product side was carrying a +2. Therefore, we need 3 electrons to show those transfers. So we write our 3 electrons, and then we finish out our reaction. And that is step 2. Step 3, and this is going to get a little messy, but I want step D there. So step 3 says to equalize the number of electrons. Therefore, we want to make sure the number of electrons in both our half reactions are equal. We have 2 electrons in one, 3 electrons in the other. Therefore, the most common value is 6. So we're going to want to have 6 electrons. So in our oxidation reaction, we're going to want to multiply everything by 3 so that those electrons can get up to 6. That shows us now we have 3 coppers, 3 copper 2 plus those 6 electrons. For our reduction reaction, because there's 3 electrons and we need to get to 6, we want to multiply everything by 2. So now we have 2 NO3 minus plus 8 hydrogen plus our 6 electrons gives us 2 NOs plus 4 H2Os. Then step 4. What we want to do in step 4 is to write the full reaction, canceling out any commonalities. Our commonalities are going to be our electrons. Everything else gets added together. So look at everything before the arrow. We have 3 coppers, we have 2 nitrates, we have 8 hydrogens. After the arrow, we have 2 copper ions, we have 2 NOs, and we have 4 H2Os. And that is the full redox reaction for this particular setup. All right, here's another example just to make sure you understand what we did in the prior one. Of course, you're more than welcome to skip this example if you so choose. All right, step 1 of writing a full redox reaction is to assign the appropriate oxidation values. Pure zinc has a value of 0. In sulfate, so we have oxygen that has a -2 value. That gives us a total of -8. We want to make sure that there's -2 or 2 negative remaining. Therefore, this sulfur carries a +6. On the opposite side, zinc has a +2 because it's a simple ion. And this oxygen is also carrying a -2. That gives us -4. Therefore, the sulfur has a +4. Need to identify who's being reduced and who is being oxidized. Zinc is going from 0 to a +2. Therefore, it is losing 2 electrons, and it is being oxidized. Oxygen staying the same, so sulfur is going from +6 to +4. It is gaining 2 electrons. Therefore, it is being reduced. And we're going to isolate on those 2 elements in this particular reaction. All right, step 2. Balance the atoms in each of the reactions. So we have our oxidation reaction. Zinc to zinc 2+. Those atoms are already balanced, so we're good there. Our redox reaction goes from SO4, 2- to SO2. Because we're going to balance the oxygens in just a minute, we're just balancing the sulfur. It is a 1-to-1 ratio. We are good to go to the next step. Balance each half reaction for oxygen by adding water to the needed side. Alright, so the oxidation reaction does not have any oxygens in it, therefore we only have to balance our redox reaction. On our reactant side, there are 4 oxygens, and our product side 2. Therefore, we need to add 2 more oxygens to our product side. In order to do that, we need to add 2 waters. The next step is to balance each half equation for hydrogen by adding H+ to the necessary side. Again, our oxidation reaction has no hydrogens. Therefore, the only one we need to balance is our reduction reaction, and we need to add the hydrogens to our reactant side because of the waters on the product side. So we have SO4, 2-. We added 4 hydrogen on the product side from those waters. So now we're going to write 4H+. And then we have SO2 and 2H2O. So now we have our oxygens balanced and we have our hydrogens balanced. The next step is to balance each half equation for this charge by adding electrons to their appropriate sides. To do this, I'm going to just move things up so that we have some room. All right. So we need to balance our reactions for their appropriate electrons. So zinc was being oxidized. Therefore, the electrons need to be on the product side to represent the loss of those 2 electrons. And then for our sulfate, we need to remember when you go back and look at what is the oxidation number for our sulfur that we had worked with. Our sulfur went from +6 on the reactant side to +4 on the product side. Therefore, we have SO4, 2-, plus 4 H plus the 2 electrons that is needed to go from a plus 6 to a plus 4. And then we finish out SO2 plus 2 H2O. The next step says equalize the number of electrons. This one's really nice for us because those electrons are already equal. If you look at them, we have 2 electrons for our zinc, 2 electrons for our sulfate. So we can skip that step and go straight to step 4, where we add the 2 half equations and cancel out the commonalities. So the commonalities are those 2 electrons, and we are going to write everything before the arrow and after the arrow to write our complete reaction. So zinc plus SO4, 2 minus, plus 4 H plus, arrow, zinc, 2 plus SO2, plus H2, H2O. And there is the full redox equation from its half reactions. The last part of 9.2 is something called oxidizing and reducing agents. So an oxidizing agent accepts the electron and therefore is being reduced. It is the agent that provides oxidation to occur. We can also call this an oxidant. Reducing agents supply the electrons, therefore they're the ones being oxidized. And so and we can call these reductants. So you need to be able to identify which one's the oxidant or reductant or oxidizing agent or reducing agent. Therefore, just like we've always been doing, we need to identify what is our oxidation numbers for each. So we have a -2 on the oxygen, and there are 6 of them, and therefore we have a +3 on our iron because there's 2 of them. This carbon is pure, therefore it's 0. Iron is pure, therefore it's 0. Oxygen is -2, and it's a 1-to-1 ratio, therefore carbon is +2. Oxygen stays the same across the reaction. Iron goes from +3 to 0. Therefore, it is gaining 3 electrons. By gaining 3 electrons, it is being reduced. Therefore, it is the oxidizing agent or the oxidant. Carbon is going from 0 to +2. It is losing 2 electrons and therefore being oxidized, and that means it is the reducing agent or our reductant. And that is all there is to it. So the ability to assign oxidation numbers, knowing which one's being reduced and which one's being oxidized, that means it's the opposite for its agent.